Here.
Sorry for the mess up. Thank you for attending. Our first speaker this year is Adam from the University of Haifa. Is that correct? Haifa?
Yeah, it's fine.
Can we talk about the symbolic dynamics and group algebras?
Graph, not group.
Oh, the graph algebra. Sorry.
Thank you. Thank you. So yeah, just let me check. Okay. So thank you everybody for coming to my talk, and thank you for the opportunity to speak. I'm delighted to have several experts in the audience in graph algebras, which I did not expect, but it's very much welcome sight. Yeah, I sort of want to start with a story. This is something that I do for many of my talks. So yes, thank you. Yeah. So I'm sure that many of you sort of can appreciate the strength of category theory as a language that one can apply in order to encapsulate a lot of different kinds of mathematics together, and it has its uses. But maybe you're on the fence, maybe you're not convinced that actually considering higher categories or two categories is something that is potentially useful. Okay, so I was a skeptic. Okay, I admit this to you. But now I'm convinced that this is actually genuinely useful. And in fact, there are situations, I'll show you one of them today, where if you do not consider things from the point of view of my category theory, you're destined to make mistakes and you can't prove what you want to prove. Okay, so I would even say that it is absolutely necessary to use bi-category theory as an interpretation in order to know what to do or how to follow your nose. Okay, so this I will try to convince you of today. So let's start with something sort of fun. Okay, this is Arnold's cat map. Consider the two torus, right, which is the real line modulo the integers squared. The real plane modulo the integers squared. And you have this sort of integer matrix, which you take always modulo 1. You take the fractional parts of the result, and it's invertible. You can see if the determinant is 1, and you can sort of go back and forth. And you think of this as a picture of the torus, and you subdivide it into 3 parts. Okay? And you give each part a digit, 0, 1, or 2. Okay? Every time you start with a point, you can start applying the map. It iterates, inverse the iterates of that, etc. And you start with a point in one of these regions, and you keep track of the digits of regions that you land in. Okay? Then you get some kind of ternary expansion, right? You have some kind of bi-infinite sequence where it tells you on which patch you sort of landed on, and you notice that the dot here, like the beginning matters, right? The A0 is the original patch where you started with, and then you sort of go back and forth.
And going to the left is by the inverses, right?
Yes, that's right. So that's what makes it bi-infinite. It needs to be an invertible map. Okay. So I'm going to denote by X sub L. L is for the linear matrix over there. Yeah. X sub L is the closed subset of ternary expansions with these 3 digits. So here I'm putting the product topology on this thing. And I want you to notice that this XL is invariant under the left shift. So if I take the dot in the ternary expansion and I move it 1 slide to the right, I get the left shift. And that subset of ternary expansions that arises from this picture is invariant under this shifting operation. Okay, and it actually
Another asking a stupid question. I'm confused by an article. They say the closed subset. So like there's one uniquely determined subset, or do you choose some subset?
it's just a subset and it's automatically closed. I just wanted to emphasize the fact that it's closed.
Okay, so like a closed subset.
Yes. I mean, it's a subset of all these ternary expansions and it happens to be closed. Okay, and so it gives you a way of modeling the orbit dynamics of this picture, which is a dynamics on a continuous space, on a connected space, yeah? But you're doing it now using dynamics on a Cantor set or a totally disconnected set, right? So this is a subset of Cantor set, it's going to be totally disconnected. Okay, so you get this 3-to-1 surjection, which happens to be continuous, and I'm telling you, and this is like a non-trivial fact, okay, that by considering a ternary expansion, you uniquely determine a point. Okay, that's a property of this particular partition. It's called the Markov partition. Not all partitions have this property, but this particular partition has this property. Okay, so it defines there's a well-defined 3-to-1 surjection. Okay, think binary expansions, right? If you want like a simplified picture, think about binary expansions of numbers in the unit interval, right? They sort of cover all numbers in the unit interval in this way, also sort of similar way. But this map has a special property. It intertwines the application of the map FL with the application of the shifting operation. Okay? And that means that any sort of dynamical property that I can infer on the shift on these ternary expansions, I can then push down to have the same dynamical property on the original dynamics. Okay, this is the beauty of using symbolic dynamics, okay, to deduce dynamical properties on continuous dynamics or dynamics on connected sets. Here's my cat. Her name is Pushok. She's a Sphinx cat. Okay, Pushok means fluffy in Russian. Okay, so that's sort of supposed to be ironic. But you know, I can take Arnold's cat map and apply it to my cat, and I get all sorts of pictures like this, and you see that eventually I get back. So there's some kind of periodicity happening. Okay, because this is a pixelated picture, right? So every pixel here out of this picture has to come back to its original spot. So in some sense, I'm telling you that even a more general fact is true. The dynamics that you saw over there have periodic points being dense. Okay, that's like the mathematical formulation of what's going on here in this particular example. All right, so I want to sort of encapsulate this situation more generally using dynamics with symbols. Okay, so suppose I have a square matrix with entries in the non-negative integers. I can include 0, and I'm going to call such a matrix an adjacency matrix because immediately it's going to represent some directed graph. Okay, I'm going to assume that it has no 0 rows and no 0 columns. It'll be immediately clear why I decided to do this, okay, in a second. But the point of the matter is that I can construct is there any marker, maybe? I can construct a directed graph out of such an adjacency matrix, okay? If I have a marker, I can show you like how to do this, but it's not incredibly complicated, okay? All right. Yeah, no worries, don't worry about it. You got one?
Hopefully it looks, that's a different.
Thank you. So here it goes, right? So VA works perfectly. Thank you, Elizabeth, for the rescue again. Yes? So VA is the index set of A, right? So if it's n by n, then it's 1 all the way up to n. And EA is maybe slightly more complicated. You sort of look at triples such that alpha is an integer, non-negative integer, that's between 0 and the value of the matrix at its UV entry. Okay, so every time I have like an entry 5 in my adjacency matrix, I add 5 edges whose source, so these are edges, right? So whose source is U, sorry, and whose range is V. Okay, so that's how I construct a directed graph out of an adjacency matrix. Pretty simple. I can define the so-called topological two-sided edge shift. How do I do that? Exactly the same way I did XL. How do I do it? I take the edge set, which is finite. All my matrices are finite. All entries are finite. Okay, you should know this for my talk. I mean, not in general, by any means. So I take the product of the edge sets. That gives me, with the product topology, some contour set. Okay, and I consider the subset of bi-infinite paths in this graph. Okay, this is called the two-sided topological edge shift. Okay, so why is it called the two-sided topological edge shift? Because there's a shift, just like in the previous example that we saw. Okay, I just shift one time towards the left. And in the example that we saw previously, turns out there's an adjacency matrix that represents it. In what way? If I take B to be the 3 by 3 matrix that's given thusly, that matrix, I claim, with this dynamics, with the shifting dynamics, is the same shifting dynamics that we saw previously with the ternary expansion. Okay, how do you construct it? You start with a patch, you apply the map to the patch, and you keep track of which other patches you intersect. That's how you get the matrix. Every row of such a matrix. Okay, very simple. And this matrix happens to be primitive. It means that some power of it, all the entries are positive, strictly positive, okay? And that's going to be important for something I'm going to say next. I just want to emphasize no zero rows, no zero columns just allows me to not have to stop. When I try to create a bi-infinite path, if I have a sink or a source, I have to stop at some point, right? So that's why I need no zero rows and no zero columns, okay? Okay, so what I'm saying here is there's a homeomorphism between the ternary expansion set and this subshift two-sided edge shift that intertwines the shifting operations, okay? So I can put this nice example that we started with in a much broader context of the so-called subshifts of finite type. Okay, these are called two-sided subshifts of finite type. And the point is that from the matrix, you can infer dynamical properties of these subshifts of finite type. For instance, this system has a dense orbit, right? There's a point such that if I take forward and backward iterates of that point via the shift, I get a dense subset. That happens if and only if the matrix is irreducible. Okay? And it happens to be something called topologically mixing. I'll tell you what that is in a second. That's another dynamical property. If and only if the matrix is primitive. I already said what primitive means, right? Some powers have.
Say what it means essential.
Essential just means no zero rows, no zero columns. Oh. Yeah, that's essential for me. Okay? And topologically mixing means that for any two open sets non-empty, there's some iterate of one that intersects the other. Okay? It's stronger than having a dense orbit. Okay? So this is great. From the matrix, we can see dynamical properties of the systems. And then we can infer these dynamical properties on some connected dynamics or dynamics on a connected space. So we would like to compare when such subshifts of finite type, when two models, dynamical models like this, symbolic models, are the same. So that leads us to the notion of conjugacy of such models, right? So a conjugacy means that these two spaces, these two shift spaces of A and B are homeomorphic in such a way that they intertwine the shifting operations. That's the strongest form of equivalence between such dynamics. But there is something else. It's called eventually conjugate, which means that starting some number, iterations of the shifts starting from that number onwards are conjugate, potentially via different homeomorphisms. Okay? This is important. Because if it was all the same homeomorphism along the way, that would have just been conjugacy. Okay? But it's not clear at the moment that these things are the same, right? So in our attempts to understand, to maybe try to find calculations, like ways of determining computably when two subshifts of finite type are conjugate, Williams introduced the following two matrix formulations. In 73, if I have two essential matrices, I'm going to say that they are shift equivalent, and I'll denote this by A tilde B. If there are rectangular matrices with values in the natural numbers, including 0 potentially, such that if I do RS, I get some iteration of A. If I do SR, I get some iteration of B, and R intertwines A to B, and S intertwines B to A.
It kind of looks like more von Neumann, doesn't it?
It does, yeah, a little bit. So you should think of R and S as some kind of morphisms, maybe. Okay, and the fact that they intertwine A and B is like maybe trying to say that they intertwine the shift in some vague sense, maybe not exactly. Okay, but I can't like reconstruct A and B on the nose, I can only reconstruct iterates. Okay, which should already raise a light bulb in your head. And strong shift equivalence means that they are in the, of lag M, means that they are in the mth transitive closure of shift equivalence of lag 1. So this is called shift equivalence of lag M. If M was equal to 1 here, I could just say that the shifts are conjugate. But I can also say that the shifts are conjugate if I do this M many times. Okay, I sort of intertwine, maybe I should write this down. So I have R1 up to Rm and S1 up to Sm, such that A is R1 S1, S1 R1 is R2 S2, and so on and so forth. Yes, until Rm Sm is equal to B. Okay, so every time I switch the order of multiplication and I do this m-fold many times, and I get from A to B. Okay. So Williams, why did he come up with these matrix formulations? They exactly encapsulate conjugacy, that's strong shift equivalence, and eventual conjugacy. That's shift equivalence. Okay, that's why you have these iterates here, because shift equivalence is something that's eventual conjugacy. Starting some iterate, they are conjugate henceforth. Okay. Great. So Williams' problem, which is like going back to the problem of decidability of conjugacy. So, you know, one of the most fundamental questions in dynamics when you're given two classes of dynamics, sorry, one class of dynamics and like two dynamics in that class, you want to ask whether conjugacy between these systems is something that is decidable. Meaning that there's an algorithm that terminates and tells you whether or not these two systems are conjugate.
So can you remind me what this tilde means?
The tilde is shift equivalence,
Shift equivalence.
and Kong is strong shift equivalence.
Okay.
And so Williams said, okay, we have a good reason to believe that shift equivalence, the one with the iterates, is something decidable. In fact, it was proven a couple of years later by Kim and Rausch that shift equivalence is in fact decidable. There's an algorithm terminating, telling you whether or not two subshifts of finite type are eventually conjugate. So I want to ask, is eventual conjugacy the same as conjugacy, or equivalently, by Williams' theorem, is shift equivalence the same as strong shift equivalence? Here's a nice example. Consider the following pairs of adjacency matrices. Here's AK and BK. And it is known that AK and BK are shift equivalent for any k greater than or equal to 2. Okay. And it's known that AK and BK are strong shift equivalent for k equals 3. For k equals 2, it's automatic. Okay. But for and for k equals 3, it takes lag 7, meaning I have to take 7 such pairs of matrices to get from A3 to B3. Okay. For k greater than or equal to 4 people, it's not known if they are strong shift equivalent. Okay. I think that this is ridiculous. Look at these matrices. They are so simple. Okay, like the B4 has entry 12. Okay, maybe that's a little big, but it's still like pretty small matrices, small size, the entries are not too big, and we still cannot tell whether they are strong shift equivalent. I am embarrassed to tell you this, but it is the truth. So, you know, we can't tell conjugacy here, but the situation is actually far worse. Shift equivalence does not imply strong shift equivalence. This is a counterexample by Kim and Rausch. Okay, there is a pair of primitive 7x7 matrices A and B, which are shift equivalent, but not strong shift equivalent. Okay, and the invariant that they use to come up with this counterexample is very, very difficult to get your hands on. It's not clear how to, the experts, I think, would agree that it's difficult to understand. They sort of have to satisfy a bunch of conditions, And, you know, what Williams' problem has become nowadays is to find maybe computable obstructions to strong shift equivalence while merely assuming shift equivalence, or to try to understand better, or coming up with more counterexamples to this Williams conjecture, or Williams problem. Okay, so considering how difficult this problem is, we would like to be able to find any means that we can, anything that we can, to measure the obstruction to strong shift equivalence while merely assuming shift equivalence, which is the computable thing, okay, or decidable thing. Okay, so let's try a new approach. In 2022, I came up with together with Carlson and Eilers, I came up with the following. Well, not the following. I'm not going to tell you what it is right now. I'll tell you later in the talk. But we came up with some intermediary equivalence relation, something that's implied by strong shift equivalence and implies shift equivalence. Okay, we called it aligned shift equivalence. And in a research exposure week for undergraduate students, we asked the following questions. Is this intermediary equivalence relation? Well, we sort of defined it, but it wasn't even clear that it was an equivalence relation. Was it even an equivalence relation? It wasn't even clear, right? We came up with it. And does it imply strong shift equivalence? Is it the same as conjugacy of the subshifts of finite type? And finally, can we detect this new equivalence relation for A3 and B3, which I remind you take lag 7. They take 7 of these pairs. That makes to get from one to the other. Okay, so with Soren Eilers and an undergraduate student, we managed to show using a computer program that in fact A3 and B3 are aligned shift equivalent with lag 7. I haven't told you what aligned shift equivalence, but it's a lower lag, okay, which is an advantage from a computational point of view. And combined with this result, which is a combination of results from this original paper and a later paper with my PhD student Pilic and Efren Ruiz, we were able to show that strong shift equivalence is the same as aligned shift equivalence, in fact. Okay, so we can verify aligned shift equivalence, which is the same as strong shift equivalence with a lower lag. Okay, so you see, there already is an advantage computationally to considering this equivalence relation as opposed to strong shift equivalence, which is kind of complicated if you think about it for a second. Yeah, yeah.
So with the 7 number before, is that you just know 7 matrices, or you know that
we know 7 matrices? We don't know anything lower.
Okay.
It's hard.
But it might be 3.
Yeah. It might be 3. Yeah, yeah, it might be. In fact, the shift equivalence between them is with lag 3, but the strong shift equivalence between them is lag 7. Yeah, you might have to double the lag in general. I don't know. I mean, it's difficult to tell. These are like really hard problems, and so somehow finding this with lag 3 sort of simplifies the calculation significantly. Okay.
Don't you assume all the time that these matrices are square?
Yes.
Okay, because I'm confused by saying that they are square matrices. They're always square. What you really assume that they are essential.
Yes, that's right. I guess I am also considering rectangular matrices some of the time, so I wanted to emphasize that these are square. Okay. All right, so how did we come up with this? How was this discovered? The answer is algebra. Okay, this leads me to von Neumann's philosophy. Von Neumann's philosophy says, okay, you want to detect analytic properties, topological properties, not just algebraic properties or combinatorial properties. Maybe you want to consider topological algebras, or von Neumann algebras, or C-star algebras. And this has been quite successful. It goes back to Mori and von Neumann. They came up with von Neumann algebras, and they were able to come up with many interesting analytic invariants for infinite groups, many equivalent characterizations of amenability for groups, for instance, that were later used in several works. Another example of this, I think this is pretty canonical, Van Jones won the Fields Medal for discovering new invariant for knots by considering something called a subfactor or subfactors of von Neumann algebras. Okay, sort of associated to knots these so-called subfactors, and then you could extract from there some kind of polynomial. It's called the Jones polynomial for knots, and it's now used. It's considered like a very useful invariant for distinguishing knots that we just did not know about before. Another sort of nice example is the work of Giordano, Putnam, and Scow. They sort of consider dynamical systems of the following form. These are called minimal contour systems. It means you have a homeomorphism on a contour set, which has no non-trivial, non-empty, non-trivial proper closed subspaces that are invariant under the homeomorphism. Okay, so the question about these guys is like, when do they have the same orbits? When is there a homeomorphism between contour minimal systems that maps one orbit to another? Okay, and this was open for many years, and eventually, by using K-theory of cross products of C-star algebra, yes, could you imagine? They came up with a group, it's called a dimension group, that they could associate to these contour minimal systems, and by calculating that dimension group using some kind of Brattley diagram, they could distinguish up to orbit equivalence these contour minimal systems, completely resolving the problem. Nowadays, everything has been stripped, right? The Jones polynomials, you can forget about von Neumann algebras. The Giordano, Putnam, and Scow result, now there's a direct proof. And so you may ask, why do I need the operator algebras? And so I answer, how would you have discovered the invariant? How could you see in the dark where you don't have anything you can lean on? Okay, so this is the von Neumann's philosophy. It says, use when you don't know what to do, when the problem is very, very difficult. What do? Operator algebras. Algebras, not just operator algebras. Algebras and operator algebras together, you can use them to come up with either combinatorial or analytic invariants for various types of problems that are considered extremely hard. Okay, and maybe you can draw insight that you would have otherwise not been able to draw. Okay, so this is the point that I want to make. So that brings me to the definition of a graph algebra. Okay, these are adjacency matrices that I have discussed so far, and I can associate to them a directed graph, and I'm going to use that directed graph to construct an algebra. It's called the Leavitt path algebra. I'm going to stick to Leavitt path algebras over the complex numbers, but of course you can define them over an arbitrary field. And they are just universal involutive algebras over the complex numbers that are generated by three types of symbols: vertices, edges, and reverse edges. These are the E stars. Okay? So now it's just a free algebra, right? There's no relations. Let me tell you what the relations are. If you multiply two vertices, you get the same vertex unless they're different, in which case it's 0. Source and range of edges, like if you multiply them by the edge correctly, they sort of behave in a natural way. And the same for the inverse, only in the opposite order. I don't want to think about it as an inverse, but you should think about it as an edge going in the other direction. When you multiply an edge by its adjoint or by a star, you get the range of that edge unless the edges are different, in which case you get 0. And then finally, you can reconstruct a vertex by taking sums over an edge times its adjoint when you look at all edges emanating from that vertex.
Okay. A regular verb.
My matrices are finite and sourceless and sinkless. Everything is regular. Okay? But thank you. Yeah, you may detect other things I'm sweeping under the rug later, Piotr, I assure you. Okay, so, and the graph C-star algebra is constructed as follows. Okay, you take the Leavitt path algebra, you embed it in some way, which I'm not going to tell you about. You embed it in some way into bounded operators on Hilbert space, and you close it up under the operator norm.
That is the same as the universal complete.
Yes. I'm not going to tell you how to do this. Not all ways to embed would work, but many ways would. Okay, and the point is you have some star homomorphism from the Leavitt path algebra into bounded operators on Hilbert space. Many star homomorphisms which are injective. You use that to sort of push the Leavitt path algebra into bounded operators on Hilbert space. You complete it, you're closing it up essentially in the operator norm, and you get a C-star algebra. Okay? What is the advantage? C-star algebras, well, they're norm closed, adjoint closed, subalgebras of operators on of bounded operators on Hilbert space, And on top of algebraic information, they also encapsulate some analytic data. Let me exemplify this. If you have an element in a pure algebra that is not necessarily closed, you can apply a star polynomial to that element. It's like if you take an involutive algebra, you get another element in the algebra. That's fine. The advantage, or one of the many advantages, but it's also a disadvantage if you think about it carefully. For C-star algebras, is that you can take an element that commutes with its adjoint, that's called a normal element, and you can apply a continuous function to that element, which is defined on the spectrum of that element. And you still get an element in the C-star algebra. Okay. This is something that will fail, generally speaking, for a pure algebra. Okay, so in some sense, pure algebras, okay, so that's an advantage to C-star algebras. On the other hand, pure algebras are able to detect more than C-star algebras, right? Because as soon as you close up the C-star algebras, you have maybe less data that you can see by closing it up, okay? So I will need to tell you about some of the extra structure that I'm going to consider. I'm going to try to encapsulate this whole problem about strong shift equivalence in terms of these graph algebras and graph C-star algebras. So given a path mu, so a path is like a finite sequence of concatenatable edges, right? Such that the ranges and sources sort of match, right? I'm going to denote by absolute mu the length of such a path. And I'm going to get something called a Z grading of the Leavitt path algebra for every natural number, sorry, every integer. I'm going to get a graded subspace. It's the linear span of mu times nu star, where the difference in length is fixed. Okay? This is a potentially infinite dimensional subspace. Okay, this is an infinite dimensional algebra. Okay? And you can close it up inside the C-star algebra with this norm that you have on it. And that gives you a grading of the Leavitt path algebra and of the C-star algebra. What is a grading? A grading means that I take a component in the nth component and the mth component, I multiply them together, I land in the n plus mth component, right? In particular, the zero graded component is a subalgebra.
And I think your assumption is it's strong grading.
Yes, I specifically put here a topological grading.
Yeah, but it's strong, so
Oh, saturated, you mean?
yeah.
Yeah.
Well,
Okay.
algebra is strong.
I will, yeah, okay, thank you. So, theorem of Cuntz and Krieger. If A is a non-cyclic permutation matrix, yeah, let's say n by n, I can encapsulate the dynamical properties that I spoke of earlier in terms of properties of the algebras. A is irreducible if and only if the graph C-star algebra is simple. And A is primitive if and only if the fixed point algebra, or I should say, the zero graded component, is simple. Okay? So this goes in line. So what I'm trying to do now, I'm trying to classify these algebras. I'm trying to say when are two such for different matrices are isomorphic in certain ways. And that goes hand in hand with something called the classification program of Elliott for simple C-star algebras. Okay, it's like more complicated than the simple, more adjectives that one has to put there. But let me not get into that.
Nuclear, unital, and what else?
Nuclear,
It's
UCT, separable,
separable, yes.
Z stable, not nuclear, finite nuclear dimension. Anyway,
Okay.
so I want to consider two new equivalence relations that are coming from considering these algebras. Okay, here are these relations. I will write tilde between the Leavitt path algebras of A and B if they are graded isomorphic, and I will write tilde between the graph C-star algebras of A and B if they are graded star isomorphic. Here's a theorem of Cuntz and Krieger in one direction, and Krieger and Nazrat in the other direction. So they land in between, I want to say, in between strong shift equivalence and shift equivalence. Okay? So the fact that strong shift equivalence implies that the Leavitt path algebras are graded isomorphic and the graph C-star algebras are graded star isomorphic, I think this is Hazrat and Cuntz and Krieger. And then the other direction uses K theory. Okay, you can actually detect through K theory, you can detect shift equivalence. Okay, so that needed for graph C-star algebras, that needed the work of Krieger, and for Leavitt path algebras, that needed work of Hazrat. So, Hazrat's conjecture. Shift equivalence is the same as the Leavitt path algebras being graded isomorphic, and the analytic version of Hazrat's conjecture says that it's the same as the graph-C-star algebras being graded star isomorphic. Okay, I just want to point out something, okay, before I continue. Having these intermediary relations is exactly what we wanted. Okay, we're trying to measure the obstruction of strong shift equivalence while merely assuming shift equivalence. So if I have some kind of intermediary relations like this that are coming from the algebras, I would like very much to classify them, because then I could come up with intermediary relations in terms of the matrices maybe that would help me distinguish in new ways strong shift equivalence from shift equivalence. Okay, so that's the advantage of considering these algebras. They give rise to equivalence relations that are strictly, well, not strictly, but in between, and now we have to orient them. Okay, that's the idea. So Hazrat is saying, Rusbe is saying that these intermediary relations are only going to see shift equivalence. Okay. And now, Bradley and Kishimoto, many people have worked on this, like Abrams, Ara, Cortines, Kuntz, Eilers. The list goes on. There's a specific result that Bradley and Kishimoto that came out before this conjecture was made for the graph-C-star algebras. I'll get to it. So yeah, analytic classification in the primitive case. That's what I want to talk about next. So, classification of graph-C-star algebras, that's sort of with additional structure is sort of related to classification via the Elliott program, and there is an equivariant sort of classification machinery via equivariant K-theory or graded K-theory that you can apply. But graph-C-star algebras and Leavitt path algebras, they're not simple in general, so you can't quite apply this machinery in the simple case that they have for C-star algebras. Okay? However, there's this result of Eilers, Resthoff, and Sorensen. You have two adjacency matrices. The graph-C-star algebras are isomorphic, not necessarily in a graded way. Yes? If and only if you can deform A from B via a prescribed set of moves. I apologize. I'm not going to tell you what these moves are.
So it's very important for me. Now, do you have this theorem under these assumptions about graphs that you are making? That no sources, no things fine.
Yeah.
Right, okay, but if I want to have arbitrary graphs,
We don't know. Beyond the unital case, we don't know. Unital just means that the matrices are finite
I'm
size.
happy with unital, but I'm not happy with the lack of infinite emitters.
Okay, fine, fair enough. I mean, but here these moves, these so-called graph moves or moves that you can apply to the matrices, they so somehow come from these, from the definition of strong shift equivalence. But there's more. There are things that do not necessarily come from the dynamics or from the strong shift equivalent picture, like something called the Kuntz splice. Okay, so these are they can become pretty complicated.
Can you decipher outspeed, inspeed, and then the rest is what?
C is Kuntz splice, P is the poulet, I think, and R is reduction. Okay, so this is like a top tier result. It was, sought for many years. People wanted to know exactly how to classify these things. It was very, very difficult. In the non-simple case. In the simple case, we knew what to do, like for many years, but this is specifically in the non-simple case. So in the graded scenario, when the zero graded component is simple, or equivalently when the matrix is primitive, there are deep dynamical tools of Bradley and Kishimoto and Evans and Kishimoto, which give you some kind of an equivariant analog of Elliott's classification. They show the following. In fact, to primitive matrices, they are shift equivalent if and only if the graph-C-star algebras are graded star isomorphic. Immediately, I want to say, before you say anything, there is no known analog for this result for Leavitt path algebras. Okay? They use continuous functional calculus very heavily. Okay? Which is unavailable for Leavitt path algebras. Okay?
It's all right, just note that you don't have shift move in your list.
What do you mean shift move?
Well, there is a move which gives you an isomorphism between graph-C-star algebras when you apply a certain move, which is called a shift. You take a while to describe it, but
Okay,
Shift.
maybe you can tell me about it. Yeah,
Okay.
I may have missed something. I mean, the expert knows best.
Yes, because this doesn't preserve the grading. Okay, I know.
No. Here.
Here you do. Shift does not preserve the
Yes,
grading.
shift does not. Yeah.
Yes, it's our
There are far fewer moves that preserve the grading. Yeah. Okay. Thank you, Elizabeth. Third time now.
Yeah, please dispense it.
So classification via graded homotopy equivalence. We can't quite solve Azrat's analytic version of Azrat's conjecture, but we can solve it up to homotopy. So what do I mean by that? The graph C-star algebras, they have a topology on them, okay? Which makes it transparent what it means to be connected via a path, okay? I can talk about connectedness via, or path connectedness, because the C-star algebras are now topological spaces, yes? So what do I mean by graded homotopy equivalent? It means that there's a pair of star homomorphisms, one from C-star of A, the graph C-star algebra of A into the graph C-star algebra of B, and the other tau from the graph C-star algebra of B to the graph C-star algebra of A, okay, such that the composition in any order can be you can find a path of graded homomorphisms, okay, graded endomorphism, right, that get you from this composition to the identity on each one of the graph C-star algebras. Okay, that's called homotopy equivalence, and it sort of makes sense. What I really mean is that whenever you plug an element there, right, now you're in the C-star algebra, you have a topology, then there's a path that maps you to the correct element for every element.
So would I be right to guess that this graded homotopy preserves graded K groups?
Yes, exactly. That's one of the observations. Yes, indeed. I'll say something about that like right after I phrase the result. So this is our main result. Suppose you have two essential matrices, then they are shift equivalent if and only if the graph C-star algebras are graded homotopy equivalent. I should mention that there's a result of Guido Arnon, okay, which does the same under the assumption of simplicity of the zero graded component, or which is equivalent to permittivity of A and B, but you have to define homotopy differently, right? In the purely algebraic setting, you don't have a topology, you have to define it in a different way. It's sort of some kind of transitive closure of something. It's more complicated. It's not as natural, okay? For instance, I understand that it's not a K1 invariant, okay, which is kind of surprising. So this notion of algebraic homotopy does work. We know less about it, but
Wasn't Karoli defining such a algebraic homotopy?
I don't know.
His book on K theory and
Algebraic K theory. Yeah. So I would imagine. That's what Chaim Shochat always tells me, that
he does all K theory.
Yeah. Okay. All right. So yeah, how do you prove something like this? First, you make Piotr's observation. K theory is a homotopy invariant. Graded K theory is a graded homotopy invariant. Okay. And so by Krieger's corollary, which sort of connects the shift equivalence to graded K theory, we know that graded homotopy equivalence would imply a shift equivalence. Okay. The other direction is more complicated. That's the hard direction. Okay. And it requires a quantization of this so-called aligned shift equivalence that I spoke of, sort of alluded to. I didn't really define it, as well as a bicategorical interpretation of it. Okay. And it answers this question that Soren Eilers gave me when I was a postdoc at the University of Copenhagen. This question sort of was, can you characterize shift equivalence in terms of the graph C-star? Give me any way of doing this that's sort of symmetric.
So SE stands for Soren Eilers.
Among other things. Among other things. Yes. Great. So yeah. So I was sort of pleased with this. Let me explain some elements of the construction and the proof. Okay. So instead of considering these rectangular adjacency matrices, let's turn them into bimodules. Let's linearize them. That's like first quantization, if you want. Okay. So whatever it is that I did here for a square adjacency matrix, I can do the same thing for a rectangular matrix with values in the natural numbers. Okay, including zero. So here's what I do. I just do the same, right? Suppose I have a rectangular matrix, which is a matrix U times V matrix, okay, with values in the natural numbers. I construct the analog of what would be the edge set of that matrix, okay, with range and source the same way that it is written here, yeah. And then we construct a so-called bimodule. We linearize, right? We consider functions on this edge set, and we can multiply from the left and from the right by functions on the vertices, by precomposing with the sources and edges correspondingly. Okay, so this is just like a bimodule over the complex numbers. At this point, it turns out that balanced tensor product corresponds to matrix multiplication. Okay, so if I wanted to encapsulate matrix multiplication coming, let's say, from shift equivalence, I can pull this into the world of bimodules. Okay, and these bimodules are now topological. I mean, I have a topology on the complex numbers, right? So, and it's connected, which is going to be another advantage. So, you know, anytime I have an isomorphism of edge sets, so what is an isomorphism of edge sets? It's just a bijection that preserves the sources and ranges. Okay, that it's like a graph, directed graph homomorphism. Okay, and so every such edge set homomorphism, or I just want to consider isomorphism in this picture, induces an isomorphism of the bimodules, but not vice versa. Why? Because I can take an edge with the given source and range, and I can map it to a linear combination of such edges in the other side. Okay? I would like to call this an entanglement of edges. Okay? It's an entanglement mixture of edges. Why do I call this entanglement? The reason is that I would like to disentangle it. Okay? And oftentimes these bimodules are actually, in this isomorphism is a unitary isomorphism, so it actually sends you an edge from an edge to a linear combination of edges such that the coefficient squares sum up to 1. Okay? So the source and range are fixed always for these. So there's a bunch of unitary, okay, that you are getting there. And I want to turn these unitaries into something that's just a permutation matrix. Essentially, that's what I want to do. And it's not clear how to disentangle and if it's possible at all, but this is actually an advantage because now I can move things continuously inside the bimodule. It's not just discrete information, it's continuous information. Okay. So, quantized aligned shift equivalence. If I have two essential adjacency matrices, we're going to say that they are module aligned shift equivalent if there are rectangular matrices R and S with values in natural numbers satisfying n bimodule isomorphisms like so. Okay, don't be alarmed. It's a lot of information to take in. Let me just say that the mere existence of these four bimodule isomorphisms is just shift equivalence by itself. It's equivalent to saying shift equivalence. Okay, so some multiplication of the matrix, right? Because tensoring, balanced tensor product of these bimodules correspond to matrix multiplication. Okay, so these are just some identification between matrices that I push up to the category of bimodules. Okay, but now I'm asking for more. I'm asking that these maps satisfy an alignment condition. Okay, this is the alignment condition. Don't worry if you're confused. So am I. Okay, the point is that we saw this and we couldn't say exactly what it meant. For many months, we asked algebraists, category theorists, they couldn't tell us until we asked Ralph Mayer, and he told us this is just an isomorphism of this composition with the identity in a bicategorical sense. Boom. And from there, everything became clear because bicategory theory works well with homotopy. You have all these functors that Ralph Mayer, together with Camila Zenem, sort of constructed for us. And we can push homotopy through these functors. So here's the important observation here. It's that shift equivalence is the same as asking for this, only that the red equalities over there are up to homotopy instead of equality. So this is, with the red equalities replaced by homotopy, this is called homotopy shift equivalence, okay? And this homotopy shift equivalence is the same as shift equivalence. Turns out. Okay? Yeah? Yeah? And now, it's a bicategorical notion, hurrah, right? So we can push it through this functor of Ralph and Camilla. It's called the Cuntz. It's not called a functor anymore because it's not a category theory notion. It's called a homomorphism between bicategories. Okay, so we push it through the Mayer-Zenem homomorphism of bicategories, and we get our result essentially. Okay, so this small observation completely knocked all the cards. Okay, so we have a hierarchy of classification of relations between strong shift equivalence and shift equivalence. Here's how it looks like. We have islands of understanding. Okay, here is the island of strong shift equivalence. Okay, the same as aligned shift equivalence of A and B, which I haven't yet told you. So don't worry about it. It's like not important for the purpose of this talk. And then we have an island of shift equivalence. Okay, the same as homotopy shift equivalence, which is the same as homotopy, graded homotopy equivalence of the graph C star algebra. Okay, and in the middle here we have this module aligned shift equivalence, which is sort of a potential obstruction. So if I wanted to show that shift equivalence implies strong shift equivalence, I would have to go back through some of these arrows, right? What is the obstruction here? What is the obstruction here from this passage to this passage, right? I've now made the picture a little more clear in the sense that if I wanted to find an obstruction for shift equivalence, for strong shift equivalence while merely assuming shift equivalence, I can try to see if I can find an obstruction of reverting these two arrows instead. Okay. So yeah, homotopy shift equivalence is a relaxation of this quantized version of aligned shift equivalence, as I told you. And so let me just conclude with a few future directions. I already mentioned that I wanted to revert one of these arrows, but I just want to say that I want to find an entanglement obstruction, right? So I mentioned module aligned shift equivalence. It means that the isomorphisms may not map edges to edges anymore. They may map edges to linear combinations of edges. I want to see if I can find an obstruction that tells me if that obstruction vanishes, I can disentangle this, I can turn the unitaries, all of them, into permutations, and therefore module aligned is the same as strong shift equivalence, which is the same as aligned shift equivalence, right? So here I maybe should have written ASE, because I just want to drop the N, right? That's where one potential obstruction can occur. Another place is to find maybe a topological obstruction from homotopy shift equivalence to module aligned shift equivalence. Okay, these are topological notions in the sense that they are notions about bimodules that are continuous, they have topology on them, and maybe there's some kind of topological obstruction that doesn't allow you to sort of make a homotopy equivalence into something that is an actual equality. Okay, so that's a rigidity question, homotopy rigidity question. And finally, I'm hoping together with Ben and Efren, we have a joint grant on this. I'm hoping this is Benjamin Steinberg and Efren Ruiz who's worked with me on this. We're hoping to do some similar things for self-similar algebras arising from self-similar groups. So all of this sort of context actually fits very, very naturally into the context of self-similar groups, Steinberg algebras, and Kuntz-Pimsner algebras, if you know what they are. And you can use them to study other types of objects. And these tools are sort of very robust. You know, they're categorical or bicategorical in nature, and maybe you can do like a bunch of things that you couldn't have done before. Okay. Yeah. So with this, I conclude. I think I'm out of time, so thank you for your attention.
Thank you for your brilliant talk.
Oh,
any questions so far?
Yeah, Piotr?
Well, since I traveled 18,000 kilometers to attend your talk, ask you a silly question. How can you extend all this theory beyond these graphs? And I don't mean just like, okay, now let's be infinite, blah, 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 seeing sources. How about, I don't know, topological graphs, higher graphs, and hypergraphs?
Many of our techniques work for general C-star correspondences, like the bicategorical tools.
Topological graphs should be okay.
Yes. The bicategorical tools are there. The notions of strong shift equivalence, aligned shift equivalence, they're all there for C-star correspondence. You can define them. In fact, I'm working on a paper with Menefshei Rizlu and Boyu Li, trying to do the C-star correspondence version of the things we did with Efren and Boris on aligned shift equivalence being the same strong shift equivalence, etc., and all that stuff. It's a lot more difficult.
Of course.
Yeah, I mean, there's so many more examples there.
That I like the answer because it kind of indicates the naturality of what you're doing. You are not just
It's
stuck.
all thanks to Ralph, I have to say. He came up with these bicategorical notions and that sort of led the way.